Hey guys, we're back with another video. Today I'm solving chemistry, October-November 2021, 9701 variant 11. Okay, so I'm gonna complete the whole series by today. The threshold for this variant was like this: A was at 22, B was at 18, C was at 15, D was at 13, and E was at 11. So you guys need to understand that this took place during COVID, so everyone's prep wasn't up to the mark. That's why the threshold was devastatingly low. Okay, this isn't an accurate representation of your major series that's coming up next month. So according to this threshold, the A star is hidden and it should be at somewhere like 40 minus 22, 18 plus 9, 31, at around 31. The 90th percentile is located at the middle of the highest mark, and yeah, in between A and the highest mark possible, which is 40, right? So by the way, there are a few changes to the paper from next year. This won't be, the duration won't be 1 hour anymore. You'll now have 1 hour 15 minutes. Okay, this applies for bio, chem, bio and chem both. Physics always had 1 hour 15, but now the Cambridge just wants consistency. You're gonna have 1 hour 15 minutes for chemistry and bio both. Okay. Also, one more thing, we don't have section B anymore in the content. That is why I'm not going to solve those. I haven't solved those either in the May June 2021 series. Okay, so I'm just going to solve question 1 to 30. But if you do want those, I'm gonna do a separate video on that. Okay, for questions 31 to 40 for the whole 2021 series, right? March, Feb, May, June, and ON combined. So just let me know if you want that in the comments below. But that isn't in your syllabus anymore, so I would recommend not doing them. All right. So let's begin. Starting with question 1. Um, what do we have over here? The mass spectrum of a sample of neon is shown. The relative abundance of each peak is written in the brackets above it. What is the relative atomic mass of this sample of neon? Okay, so it's gonna go like this: 100 into 20 plus 21 into 0.3 plus 22 into 8. It should be divided by 100 plus 0.3 plus 8, because that's the total abundance, right? So 100 into 20 plus 21 into 0.3 plus 22 into 8 divided by 100 plus 0.3 plus 8. That gives us a value of 20.15. Okay, so remember, it's not always going to be divided by 100. Remember that in the denominator you're going to have the total abundance, so you need to add these up to get the total abundance. That's your denominator. Okay, so for 2 grams of ammonium nitrate decomposes to give 0.9 grams of water and a single gas. What is the identity of the gas? Okay, so ammonium nitrate actually decomposes to give water and a single gas. So we have 2 grams of this and 0.9 grams of this. If you look at the MR for this, it's 14 plus 4 plus 14 plus 3 times 16, which is 48. That's 80. Okay, so if you want to find out the moles, 2 by 80, that's 0.025. 0.025. Okay, 0.025. What about water? What about its MR? That's 80. 2 plus 16. So 0.9 by 18 is 0.05. Okay, now what do we understand about the molar ratio? The moles of water, if this is 1, look at this, 0.05 is twice that of 0.025, right? So the molar ratio of water is, the moles of water is twice that of ammonium nitrate. So now we can find out the identity of the gas, right? Because if you take away 2 moles of water from here, that's 4H and 2O. We have, from here, we have 2 nitrogens remaining and 1 oxygen. So what gas is that? That's actually N2O, right? So by balancing this equation, we got the identity of the gas, and you should also know the identity. Okay, you should have this memorized. This is important for paper 5. Ammonium nitrate decomposes to form nitrogen dinitrogen oxide, okay, or nitrogen 1 oxide, and water. Okay, which of these elements has the highest fifth ionization energy? Fifth ionization energy. Okay, so let's look at the data booklet. I have it over here. Wait. So carbon, nitrogen, phosphorus, silicon. Carbon, nitrogen, phosphorus, silicon. So we're looking at fifth ionization energy. Okay, so for carbon the configuration is 1s2, 2s2, 2p2. For nitrogen it's 1s2, 2s2, 2p3. Okay, for phosphorus it's 1s2, 2s2, 2p6, 3s2, and 3p3. For sulfur it's 1s2, 2s2, 2p6, 3s2, 3p4. This is for sulfur. Now we want to see which one will have the highest ionization energy. So typically if a shell is added, okay, typically if a shell is added, the distance between the nucleus and the shell actually increases, so less energy is required. So at the beginning phosphorus and sulfur are already excluded because they haven't have a uh, you know they have greater number of shells, so they shouldn't be part of the argument. We should only think about carbon and nitrogen over here. So now look at this. If you think about nitrogen, highest fifth ionization energy. Okay, so look at this carbon over here, 1s2, 2s2, 2p2. Okay, so for the fifth ionization energy, where are we going to take the electron from? After 4 ionization energies, it will become C4 plus, right? It's going to become 1s2 only. We are getting rid of 4 electrons from 2s2 and 2p2. So the fifth electron that I'm taking, it's going to be from the first shell, which is much closer to the nucleus. Now check this out, guys. From nitrogen, after 4 ionization energies, what do we end up with? We're going to end up with 1s2, 2s1, because we took 3 away from the 2p orbital and 1 away from the 2s orbital. We're still taking the electron from the 2s orbital, which is further away compared to 1s. That's why carbon should have the highest fifth ionization energy, because it's from the first shell. Could I clarify? So according to that logic, 3 should be A. This is a bit tricky, right? Now the ion X2 plus has the same electronic configuration as the atom krypton. So check this out. Krypton has a configuration of 1s2, 2s2, 2p6. Krypton 1s2, 2s2. Basically, it has the configuration of argon, right? Configuration of argon followed by, this is the fourth period, so 4s2 followed by 3d10 followed by 4p6. Okay, so 4s2, 3d10, 4p6. 4s2, 3d10, and 4p6. So that's what we're looking for. So 4, that's the configuration of krypton. Okay, but look at this. That's the configuration of the ion. Okay, if they wanted the configuration of the ion, A would be the answer. But hear me out. This ion X2 plus has a configuration of argon, 4s2, 3d10, 4p6. What about the actual element? The element lost 2 electrons to get to that state, if you think about it. Okay, so it lost 2 electrons to get to that state. So if we add 2 electrons, what comes after argon? After argon you have rubidium and strontium. So this is period 5. Rubidium is 5s1, strontium is 5s2. So this is probably strontium, and the configuration should have a 5s2 as well, because A is actually the configuration of the Cation, they want the configuration of the atom. That's why we need to add those two extra electrons. Okay, it's a bit tricky. Which type of interaction exists between water molecules and metal cations? So water molecules, they have dipoles, and cations like sodium ions, it's charged, right? So clearly not a hydrogen bond, because we need these three elements, NOF and hydrogen, to make that. It's basically an interaction between a dipole from water and an ion here. So it's called an ion dipole interaction. Okay, 5C. Which substance shows the greatest deviation from the properties of an ideal gas? The stronger intermolecular forces you have, the more deviation you will show. Here, the strongest intermolecular force of attraction is hydrogen bonding in ammonia. So 6 is D. 7. In order to determine the enthalpy of neutralization of a strong acid and strong alkali, 25 cm cube of 2 mol per dm cube sodium hydroxide is added to 25 cm cube of 2 mol per dm cube hydrochloric acid. The increase in temperature is 12. In a second experiment, the same method is used, but 50 cm cube of 2 mol per dm cube sodium hydroxide is added to 50 cm cube of 2 mol per dm cube hydrochloric acid. So, guys, what happened? We have actually increased the volume of both the reagents. Do you understand? Both sodium hydroxide and hydrochloric acid. So HCl and NaOH, they actually react in a 1:1 ratio. Initially it was 25 cm cube of each with 2 mol per dm cube of each. Now the molar ratio is the same, the concentration is the same, but we have 50 cm cube of each. So you know what, if you increase the volume of one of them, it wouldn't really make a change, because one would end up being the limiting reagent. Okay, but here, since we've increased the volume of both of them, right, no one's the limiting reagent. All of the HCl will react with all of the NaOH. Do you guys understand? As a result, what's going to happen? More moles of water will be formed. For example, before, you know what, that we'd get NaCl plus H2O. Now we're still going to get NaCl plus H2O, but beforehand we would be getting 25 by 1000 into 2. We'd be getting, 0.05 mole of H2O. But now we're going to get double, which is zero point 0.1 moles of H2O. So the heat actually depends on the number of moles of water produced. Since the number of moles of water produced has doubled, okay, what's going to happen? Logically, it was supposed to double as well. But here's the thing. This was a trick question. Like, the enthalpy change of neutralization, what is its definition? It is the enthalpy change when 1 mole of water is produced by the reaction between an acid and a base. For a strong acid and an alkali, it's always around minus 57 kilojoule per mole. So the answer should be B. I'll tell you why. Because even though comparatively, if you compare the heat released in this reaction, the second reaction, is twice that of the first. However, if you think about the moles, to find out the enthalpy change of neutralization, you have to divide by the number of moles, right? The number of moles in experiment 1 is n, but here it's twice n. It's double the moles. So we can actually get rid of these 2's, and we're going to end up with del H by n. Do you guys understand? It's the same value. So it's still going to be 12. Really complicated in a sense, okay? Which equation represents the enthalpy change of atomization? So basically, atomization is the enthalpy change when 1 mole of gaseous ions is produced, so these are gone, from its element in its standard state. Iodine exists as a solid, so A is wrong and C is the correct answer. Okay, it's C. Zinc atoms can be oxidized to Zn2 plus by dichromate in acid solution. Chromium is reduced to Cr. Which one is correct? So really important, guys. Chromium in Cr2O7 has a charge of plus 6. It goes to plus 3. Okay, so the electron change, it has actually gained 3 electrons, but since there are 2 chromium atoms, it actually gains 6 electrons. Okay, 6 electrons. On the other hand, zinc is oxidized from 0 to 2 plus. Okay, so it basically loses 2 electrons. Zinc loses 2 electrons. So your goal is to balance the number of electrons. This is 2. How are you going to balance 2 and 6? You just need to multiply this by 3 because 3 2s are 6. If you balance the number of electrons, your equation will automatically be balanced, okay? So in front of chromium dichromate we need 1 and in front of zinc we need 3. So the correct answer for 9 should be C, alright? Moving on to 10, the equation shows that hydrogen and iodine react to form an equilibrium mixture. A mixture containing equal amounts of hydrogen and iodine is made at temperature T1 and the composition is monitored. A graph of the results is shown. The experiment is repeated at a lower temperature. This is an exothermic reaction, guys. If you repeat it at a lower temperature, basically rate will decrease, so it will take longer to establish equilibrium. But since temperature is decreased and it's an exothermic reaction, the equilibrium will actually shift to the right hand side. Could I clarify? The equilibrium will shift to the right hand side. So if it shifts to the right hand side, the concentration of HI will increase and the concentration of hydrogen and iodine will decrease. That's the logic. So in the new one, C is wrong because it shows that the mole fraction of iodine remains the same, but that's not true. Same goes for A. In the next one, we have to look for two things, okay? They could have made this question a bit more difficult, but they didn't. Basically, we need to ensure that compared to before, iodine drops to a lower value and the steepness of this graph will be less, okay? So iodine needs to drop to a lower value. So the only option where iodine drops to a lower value is B, okay? And as you can see, it's less steeper because temperature has decreased, the rate has decreased, okay? Hopefully you guys understand. And if we repeated this at a higher temperature, what would the answer be? The answer would be D, alright? I'm not sure though, because at a higher temperature, look, the steepness is wrong. It's wrong. So this is not a correct answer. It's not right. My bad. This wouldn't be the answer for the one at a higher temperature. Okay, moving on to 11, the second part of the video. The diagram shows the Boltzmann distribution of energies for a reactant gas. For a particular reaction, the activation energy is X. Which change the diagram occurs if an effective catalyst is added at the same temperature? Okay, so nothing happens to the distribution. Only the activation energy moves to the left hand side, okay? So nothing happens to the peak. And it's not like more values, more particles will have energy than E. This remains unchanged. Okay. The value of the activation energy. Okay, it's not like more particles will possess more energy. It's not that. It's just that particles have the same energy, but since the activation energy has decreased, now more molecules have energy greater than the activation energy. Okay, but not more energy in general, right? Okay, 12. Which element requires the least number of moles of oxygen for the complete combustion of 1 mole of its atoms? Okay, so aluminium plus oxygen is equal to Al2O3. So how many do we need here? 3 by 2. Wait up. So to balance this, it's 3 by 2. So for 1 mole of aluminium, it's 3 by 4. Does this look good? I multiplied everything by half here. So 3 by 4 into 2 is 3 by 2. Yeah. And yeah, that's 3 by 2 on the right hand side. So we need, for aluminium, we need 3 by 4 moles of oxygen gas. Okay. Next, magnesium. Half a mole. Phosphorus. 1 mole of its atoms. Okay. Clearly not the answer. 5 moles of O2. Sodium Na plus O2 is equal to, probably this is going to be it, Na2O, right? So we need 2 half. So for 1 mole of sodium, it's going to be 1 by 4 O2 half Na2O. Okay, so for this we need 1 by 4 O2. So the least one is in D, 12D. Okay. Now an element 13, element Y, reacts according to the following sequence. It burns in oxygen to form a white solid. Okay, the important part is it is soluble in HCl, is also soluble in AOH. Okay, if you give excess NaOH, it is soluble. So something that actually reacts with both acids and bases. What is that called? Amphoteric substance, right? Amphoteric oxide. So clearly, 13 is C. Aluminum is amphoteric. These two are basic. This is acidic. Okay. In which list are all three compounds soluble in water? Barium chloride is soluble. Calcium chloride is not. Barium hydroxide is soluble. Strontium carbonate is not soluble. Calcium hydroxide is not soluble. Barium chloride is soluble. Barium hydroxide is soluble. Magnesium sulfate is soluble. Remember this, guys. Down group 2, solubility of hydroxides increases, solubility of sulfates decreases. Okay, so magnesium sulfate is soluble. And in D, barium sulfate is not soluble. 15. Anhydrous magnesium nitrate decomposes when heated, giving a white solid and a mixture of two gases X and Y. Y is oxygen. What is the ratio of mass of X released by mass of Y? This is the equation, okay? So Y is oxygen. So the other gas must be the brown gas, nitrogen. So the ratio of X to Y, okay? Basically, the molar ratio is 4 is to 1, okay? So since we're dealing with mass and not moles, let's think about the MR. Mass is equal to moles into MR. So here the moles is 1. 1 into 16 plus 16, 32. Here it's going to be 4 into 32 plus 14. 184, 32. So X to Y, right? That's giving a white solid and a mixture of two gases X and Y. Y is oxygen. Okay, so it's 184 by 32. 184 by 32. I'm getting a value of 23 by 4 or 5.75. So basically we need to match these values with 5.75. Try a 1 divided by 0.174. That gives us a value of 5.747 or 5.75. So A is the answer. Okay, so 15 is A. Now moving on to 16. So they basically try to trick you, okay, in 15 by giving these weird values, but you just need to check. In a series of 9 experiments to test the reactivity of the halogens, an aqueous compound, an aqueous solution of each halogen is added to an equal volume of an aqueous solution containing halide ions. Okay, guys, so as a halogen, you can you can only oxidize those halides that are below you, not above you. So you guys know the series, right? Fluorine, chlorine, bromine, iodine. So for example, chlorine can oxidize bromide and iodide, but it can't oxidize fluoride, for example. Okay. So hear me out. Let's do this. The answer is D here. This is what it looks like when the halogen is dissolved. Okay. The right one is iodine, then bromine, and then we have chlorine. in this is in an organic in hexane. Okay, this is hexane. Hexane and water are immiscible because they have different intermolecular forces. One is a polar solvent, one is non-polar. We're going to learn about this in A2, partition coefficient. The 9 resulting mixtures are then shaken separately with an equal volume of hexane. The 9 tubes are left as stands so that the aqueous and organic solvents separate into layers. How many test tubes contain a purple upper hexane layer? So remember, the purple layer is actually due to iodine. So if iodine is liberated by any chance, we are going to get the purple layer. So look at this. Chlorine won't react with chloride. So here there's no chance of getting iodine. Chlorine will react with bromide, but we're gonna get an orange solution, so it's not the answer. Chlorine will react with sodium iodide to form sodium chloride, and we're gonna liberate iodine as a purple solution. So this is correct. We have one winner. Bromine will not react with chloride. Bromine will not react with bromide. It's the same thing. Bromine will react with iodide, and we're going to liberate purple iodine. Next, iodine will not react with chloride because iodine is below chloride, so it cannot oxidize chloride. But iodine is purple itself, right? That's why we're going to see the purple color, because iodine is added to the solution, but it does not undergo any reaction. Iodine plus NaCl, no reaction, so we're going to see the purple color of iodine. Then here we are also going to see the color of iodine. Here we're also going to see the color of iodine. That's why the answer is 5. Okay, it's just that in parts 1 and 2, in these two rows, we got iodine because it was liberated. In the last row, iodine was seen because we added iodine. Okay, that's the logic. 17. Z is a compound of sodium, chlorine, and oxygen. It contains 45.1% by mass of oxygen. Z is prepared by reacting sodium hydroxide with chlorine. Which row shows the conditions used for the reaction and the oxidation state of chlorine in Z? Okay, so if you react NaOH with chlorine in cold conditions, you're gonna get NaClO, and in hot conditions, if you react NaOH with chlorine, you're gonna end up with NaClO3. Okay, so the compound contains 45.1% by mass of oxygen. Let's try this compound. 16 divided by 16 plus 35.5 plus sodium is 23 or 23.1. 23 exactly. Okay, so sodium is 23. So let's multiply this by 100. 16 plus 35.5 plus 23. 16 by answer into 100. It gives us a value of 21.5%. So this doesn't look good. Let's look at the next one. 16 into 3 divided by 16 into 3 plus 23 plus 35.5. Try this. 16 into 3. Answer divided by 48 plus 23 plus 35.5 into 100. So this gives us a value of 45.1%. Okay, so you need to memorize this, by the way, from your lectures. There are two reactions, and in the course book you can find this in the course book. Okay, so this contains 45.1%, and the conditions are hot, and the oxidation number of chlorine here is -6 plus 1 over here, so chlorine has to be +5. So 17 is in fact D. 18. Which row is correct? Ammonium molecule is pyramidal. Yes, sp3 hybridized, but pyramidal due to the lone pair. Ammonium, it receives a proton, so it's sp3 hybridized, but it has 4 bond pairs, so it's regular tetrahedral. In ammonia, we only have sigma bonds. In ammonium ion, we also have sigma bonds. Remember, you will only get a pi bond if a double or triple bond is present, right? But if you see single bonds only, it's gonna be sigma, right? So 18 is A. 19. The table describes two possible environmental consequences of adding too much ammonium nitrate fertilizer to the soil. Which row is correct? Eutrophication does occur. Increased plant growth. It does occur. So it's between B and D. Photochemical smog. So about this, what do you know about photochemical smog? Basically, Photochemical smog is a mixture of pollutants that are formed when nitrogen oxides and volatile organic compounds react to sunlight, creating a brown haze above cities. Okay, so we also have some PANs, right? It has been added to the syllabus. PNs, peroxyacetyl nitrates. Basically, you need to understand that adding ammonium nitrate to the soil does not contribute to photochemical smog. It is mainly due to um, exhaust fumes and industry fumes from the industry. Okay, remember that, guys. So remember the basics. It does not cause photochemical smog actually, but because the nitrogen is taken up by plants, it's used in the nitrogen cycle, right? But it's formed like it's converted to proteins and amino acids. Okay, it's not released as nitrogen oxide, so it doesn't contribute to photochemical smog. Okay, so 19 should be B. Hopefully you guys understand. Moving on to 20. Finally, organic. Personally, I really like doing organic. Okay, Higgs 2 in can be made by the reaction shown. Okay, this is an elimination reaction using. How do we eliminate halogen alkanes like this? Perform elimination reactions. We need sodium hydroxide in ethanolic conditions. Okay, so CH3, this compound here, CO minus, is behaving as a Bronsted-Lowry base. What is a Bronsted-Lowry base? A compound that actually accepts protons. Look at this. This negatively charged compound with a lone pair actually accepted this proton, right, to become OH. So yes, it is acting as a base. So that's true. It is acting as a Bronsted base because it is accepting the proton. By the way, it is not a hydrolysis reaction because water was not used to break any bonds. The Ci bond breaks via homolytic fission. No, 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 no. It's actually heterolytic fission because we get this iodide, and it is behaving as an oxidizing agent. Um, is it though? No, this is not an oxidation reaction. Okay, it's an elimination reaction. It's not classified as oxidation reduction or redox. You need to remember that. Okay, there's no change in oxidation number, so B is also wrong. 21. Structure isomerism only should be considered when answering this question in 21. Molecule X contains 3 carbon-carbon double bonds. 1 mole of X is reacted with 3 moles of HBr. The carbon skeleton is unchanged. How many different products are formed? Interesting. Let me show you something. Right up. Where's the snipping tool? Right. Okay. So check this. So, how many different products are formed when HBr is added? Basically, it reacts with 3 moles of HBr. An electrophilic addition reaction will occur. Okay, an electrophilic addition reaction will occur. So, if we add HBr over here, check this. Suppose here, we should only consider structure isomerism, by the way, no stereoisomerism. Okay, so look at this compound that I'm drawing over here. This is one instance. Okay, now I'm gonna attach H in the same position, Br in the same position, but now I'm gonna switch these places to BRH and HBr. Now what? Check this. Now the difference in the second stage will be, now I'm gonna add the HBr in this manner. I'm gonna add bromine here, hydrogen here, bromine here, hydrogen here, bromine here, hydrogen here. Oh, by the way, one more thing. This first compound could also be like this. Like we could have the bromines here instead. Okay, like this. Because if you look at it from this aspect, think about it. Look at the compound I drew in the beginning. Okay, look at this compound. You need to look at the priority, like you need to look at the proximity. Okay, from this hydrogen and bromine. Check this out. If you look at the bromines, it's like this. Okay, just let me draw the compounds, then I will clarify at the end. So check this. HBr. Okay. Okay, why don't I draw another figure then? That's gonna be the best. It's gonna be the best for you guys, yeah. HBr, BR, wait. HBr, BRH. Now what I'm gonna do is basically I'm gonna keep this the same at HBr, and this is gonna be changed to BRH. Okay. What about the other compound I was talking about? This one basically, BRH. Okay, followed by BR over here, H over here, BR over here, and H over here. And what about this one over here? We have H, BR. Okay. And then we have BR over here, H here, BR over here, H here. So I've drawn 8 compounds here, but the correct answer is actually 4. Okay, do you understand? There's 4. You need to figure out that out of these combinations, some of them are actually identical. Okay, so I'm gonna tell you how to figure that out. So basically, look at this. Look at this compound at the top over here. We're gonna see the proximity from this bromine. Okay, look at this. 1, 2, 3. 1, 2, 3. Okay, so the proximity from this bromine to the hydrogen actually is going to be 1, 2, 3, 4. Okay, the proximity from this bromine to the hydrogen is 4. The proximity from this bromine to that hydrogen is 3. This is not the same. What about this scenario over here? Check this. You have 1, 2, 3. Okay, so there's 3 over here again. What about this one over here? We have 1, 2, 3, 4. Okay, we're seeing bromine to hydrogen. So as you can see, it's the same for the first compound. It's the same for the first compound. Like I'm naming them as compounds 1, 2, 3, 4, 5, 6, 7, 8. Okay, you guys need to understand that these are symmetrical. They are symmetrical. Okay, so we can find this out in an easy way. I'm gonna tell you how later, but let's find it out manually first. So 4 compounds, 1 and 3 they match. Now let's look at the proximity from this hydrogen, right, to hydrogen itself. Then 1, 2, 3. 1, 2, 3, 4. Okay, then 1, 2, 3, 4. 1, 2, 3. Do you get it? So here we're getting a combination of 3 4 4 3. Now look at these combinations from hydrogen to hydrogen and bromine to bromine. I mean bromine to hydrogen as well. Hydrogen to hydrogen and bromine to hydrogen. It's 3 4 in the first one. It's 4 3 in the second one. It's 4 4 in the third one, and it's 3 3 in the last one. So these four are actually our isomers. Do you understand? That's it. Then you might be wondering, what about the ones you drew on the right hand side? Like, aren't these isomers? No, not really, because check this out. I'm going to do the same thing. Bromine to hydrogen and hydrogen to bromine. So bromine to hydrogen first. Check this. 1 2 3, 1 2 3 4. Okay, then 1 2 3 4, and 1 2 3. Hydrogen to hydrogen. 1 2 3, 1 2 3 4, 1 2 3, and 1 2 3 4. Okay, so you're going to see something interesting here. So this is 3 4, hydrogen to hydrogen and bromine to hydrogen. Okay, then this is 4 3, this is 4 4, and this is 3 3. See, these combinations match. These are the 4 combinations possible. So out of these 8, some of them are the same. Which ones are the same, you're wondering? I can actually show you. Look at the ones that are 3 3. Okay, for example, this one is the same as this. Actually, check it out. It's actually the same. It has just been flipped or rotated by 180 degrees. That's the difference. If you rotate this, okay, if you rotate this by 180 degrees, can I do it over here? You're gonna get the same compound. Alright, if you rotate this by 180 degrees, you're gonna get the same compound. This whole thing, basically. I don't think I can do it together, but yeah, if I rotated the whole thing, we'd get the same compound. So these two are the same. Then 4 4, these two are the same. Okay, what about this? Is this hydrogen to hydrogen is 4, hydrogen to hydrogen is 3. Okay, so this one is the same as this, and this one is the same as this one. Okay, so yeah, it's a bit complicated, but you need to understand that since there's no cis-trans isomerism, basically where you put the bromine and hydrogen here don't matter. That's totally up to you. Okay, you can put it anywhere. You can also invert it. Basically the 4 combinations are, one of them is like this: bromine bromine, hydrogen hydrogen. This is one of them. The other combination is switching these up, basically hydrogen hydrogen, bromine bromine. These are 2 different compounds, by the way. They are not the same. Then the other combination is basically hydrogen bromine, bromine hydrogen. Okay, hydrogen bromine. Wait, let me show you the combinations again. It's either hydrogen hydrogen, bromine bromine. This is one. Okay, then the other one is like this: hydrogen hydrogen, bromine bromine. Okay, this is the other one, because clearly it's not the same. Okay, these two are not the same compounds, the one above and below. Look, this one and this one, they're not the same. Like, I've drawn this compound, this bromine hydrogen compound over here. This is the orange one, basically. So if you keep the hydrogens above, right, look at this. The proximity from hydrogen to hydrogen is 3 here, but the proximity from hydrogen to hydrogen is 4 here. So these are 2 different compounds. Okay, if the proximity was the same, it would have been the same. Look at this: bromine to bromine, 1 2 3 4 on this side, and here 1 2 3 4. Okay, but here look at this: 1 2 3 on this side, and here 1 2 3 4 5 on the other side. Do you guys understand? So these two are actually different. And what about the last two combinations? By keeping bromine and hydrogen in the same position, basically you can alternate them like this: bromine hydrogen once over here, hydrogen bromine here, or hydrogen bromine here and bromine hydrogen here. I'm going to show that these are different compounds. Look, bromine to bromine, 1 2 3. Okay, 1 2 3 4. Bromine to bromine, right? 3 4. Now look, 1 2 3 4, 4 here, 1 2 3 4 5 here, 4 5. So it's 3 4 4 5 here. What about this? It was 3 1 2 3 4 5, and here it was 4 4. Okay, so you can choose any one to compare. Like I used hydrogen bromine and bromine bromine last time. Now I'm totally using bromine bromine. Okay, so that's the gist. I took a long time to explain this, but I just want to clarify one last time. Wait, let me clarify for you guys. Okay, so suppose, like what I'm trying to say is, since cis strands or optical isomerism does not matter, it doesn't matter where you put the bromine actually. Okay, it doesn't matter where you put the bromine. You can put it anywhere you want in the middle. I'm talking about the middle. Okay, so suppose I bring it here, bromine. I'm not going to show the hydrogen at all. It's here, but you don't need to show it. Okay, you don't need to show it. Let's not show it this time. So now let's do the combinations. Okay, it will be easier without the hydrogen. I just want to explain this to you guys properly. Okay, I don't want to make a mistake. Okay, so the first combination, bromine bromine. I've added the H here, just not showing it. Then I have bromine bromine. Then I have bromine over here, bromine over here, and bromine over here, bromine over here. These are the four combinations. Okay, so check this out. I'm gonna see the proximity on the left and right hand side. Okay, so 1 2 3 4, shortest distance. Then 1 2 3 4 4 4. Next 1 2 3 1 2 3 4 3 4. So 4 4 3 4. Now 1 2 3 1 2 3 4. Wait, did I mess up here? 1 2 3 4 5. Sorry, it was 5 over here on top. My bad. So yeah, it's 1 2 3 over here, and 1 2 3 4 here, 3 4. Now last one, 1 2 3 4, or 1 2. You can also go like this. That's 4 and 1. Should I use a different color? 1 2 3 4. 1 2 3 4 5. So this is 4 5. We have 4 5, we have 3 4, we have 3 5, and 4 4. These are the combinations basically. So that's what I'm trying to say. Okay, that the difference, and it doesn't matter where you put it in the center because you'd be getting the same combinations. So it's not 8, it's actually 4. Okay, these are all the combinations. It's a bit tricky, but according to symmetry, okay, according to symmetry you can find it out more easily, but I just gave an elaborate explanation. Okay, moving on. Structure isomerism and stereoisomerism should be considered when answering this question. Colorless liquid C5H11Cl exists as a mixture of two optical isomers. When heated with sodium chloride and ethanol, a mixture of only two alkenes is formed. What could that colorless liquid be? Okay, let's see. Alright, so it exists as two optical isomers, so clearly it has a chiral center. Okay. When heated with sodium hydroxide, a mixture of only two alkenes is formed. What could this mixture be? What could the colorless liquid be? Okay, let's try from A. Okay, so CHCl, CH2CH3, CH2CH3. Basically, this compound is not it's not a chiral compound. It does not have a chiral center, so 22 can't be A. Moving on to B, we have CHCl, CH3, CH2, CH2, CH3. For this we have a chiral carbon. Okay, this meets the first criteria. When heated with sodium hydroxide and ethanol, a mixture of only two alkenes is formed. Okay, cool. So if we heat it with NaOH in ethanol, ethanoic NaOH, we're gonna get an elimination reaction. So we have two possibilities: either this CH3, CH2, 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 or on the left hand side CH3, CH2, CH, CH3, CH2, CH, CH, CH3. So hear me out. There's no cis-trans isomerism here. We only get one compound, but there's cis-trans isomerism in this compound, so we get two. In total, we have three compounds for this, okay? So that is why B cannot be the correct answer, okay? So that's why we're excluding B. Moving on to C. CH3, CH2, C, Cl, CH3, CH3. Not chiral again, so this is excluded. So clearly our answer is D. Let's see how. CH3, C, CH3, H, CH, Cl, CH3. This is our chiral carbon. After elimination, we're gonna get this on one side. CH3, CH, CH3, CH, CH2. This doesn't have cis-trans isomers, so only one over here. Then CH3, C, CH3, double bond, CH, CH3. This one doesn't have cis-trans isomerism because this carbon has two of the same groups attached, two methyl groups attached. So we only get one isomer from here as well. 1 plus 1, 2 in total. So the answer is in fact D. 23. When 2 bromopropane, 2 methylpropane, it's a tertiary halogen alkane. And if it reacts with aqueous sodium hydroxide, nucleophilic substitution will take place, but this is SN1 because it's a tertiary. It's a tertiary halogen, no? Alkane. Do you understand? So in the first step, remember in tertiary, in unimolecular or SN1 reactions, a carbocation is produced, okay, by heterolytic fusion. So C and D are wrong because the first step is a slow step and the carbocation is produced, and the arrow should point towards the direction of bromine because we get a bromide anion. The arrow should point in the direction of the element or the species that gets the electrons. So 23 should be B. 24. When an organic compound Q is treated with phosphorus pentachloride, fumes of hydrogen chloride are evolved. When Q is warmed with acidified aqueous potassium dichromate, the solution turns green. Okay. So compound Q is an alcohol or carboxylic acid because they react with pentachlorides to form acyl chlorides and for carboxylic acids and halogen alkenes for alcohols. So Q can't be this. Q is warmed with acidified potassium dichromate. The solution turns green. It can't be the carboxylic acid because this is an oxidizing agent. Carboxylic acids cannot be oxidized. Alcohols can be oxidized. It's between C and D. But D can't be the answer because it's a tertiary alcohol. Tertiary alcohols cannot be oxidized. 24 is secondary. It will secondary alcohol. It will oxidize to form propanone ketone. 25. Alcohol Y gives a yellow precipitate with aqueous alkaline iodine. Okay, it gives a positive iodoform test. That means it's a secondary alcohol with a methyl group as a side chain. Okay, it can be oxidized to give a mixture of products, including substance Z. Interesting. Substance Z gives a red-brown PPT with fillings. So Z is an aldehyde actually. Okay, so let's look at the first criteria. We want it to be a secondary alcohol with a methyl group as a side chain. CH3, CHOH. Okay, this looks good. CH, CH3, CH2OH. This looks fine actually because it has this group which can be converted to the methyl ketone. When it's oxidized, it forms CH3CO, CH3, CHO first. Yeah. And yeah, this one looks good. It is oxidized to the aldehyde before the carboxylic acid, which does give a red brown PPT, right? A is correct, okay? Why not B though? I'm going to show you the others. CH3, COH, CH3, CH2, CH2H. This is a tertiary alcohol, okay? Also, this won't give a positive iodoform test, so that's gone. This is fine, but this is oxidized to form a ketone, secondary alcohol, no red bound PPT. This compound is a primary alcohol. This won't give a positive iodoform test. There's no methyl group, okay? Check this. This compound is like this. Okay, no methyl group. We have an ethyl group, so it's wrong. 26. What is this? Pentanthreone reacts with hydrogen cyanide to form an organic product called a cyanohydrin. Which statement is correct? The cyanohydrin, right? After reaction, it forms this compound. This is the compound initially. It forms CH3, CH2, COH, CH2, CH3, CN. This is the compound. It does not have a chiral center actually because it has same groups on both sides. It is formed by nucleophilic addition, not electrophilic addition. The cyanohydrin is formed via an intermediate which contains a COH group. No, the intermediate actually contains this group. O minus, right? This one. It's like this. So that's wrong. D should be correct. The formation requires the use of cyanide ions as catalyst. That's true. Reduction of the compound R with LiLH4 gives the compound 4-methyl pentane 2,3-diol. Okay, let's write this compound. What is this mainly? It's mainly pentane. This is the main compound. It's pentane. CH3, CH2, 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 CH3. It's actually pentane. There's basically, like, if this is carbon 1, there's basically an OH group on the second carbon, an OH group on the third carbon, and a methyl group on the fourth carbon. So this is what the compound looks like. Now I'm going to draw the skeletal formula. Okay, so how? 1, 2, 3, 4, 5. 5 carbons. This is carbon number 1. Second carbon has an OH, third carbon has an OH, and fourth carbon has a methyl group. Okay, so this is the compound formed after reduction of the compound using LiLH4. Now, what about compound R that was present initially? So think about it, guys. If you reduce, like, secondary alcohol is the reduction product of a ketone. Do you get it? So beforehand, this existed as CH3, CH3, then CO, CO, CH3. This was the compound before. Okay, so what's the skeletal of this compound? This part will remain unchanged. This will be a ketone. This will also be a ketone. And yeah, this is our carbon number 1. So this was reduced using LiH4 to get that compound on the left. Okay. So yeah, D can't be the answer because that's an aldehyde. If you're looking for the answer, 27 should be A actually. It matches. It's just inverted. Okay. Remember that it's inverted. Last few ones. Citric acid is found in lemon juice. Which volume of 0.4 mole per dm cube sodium hydroxide solution is required to neutralize a solution containing this? Okay. So remember, sodium hydroxide can't react with alcohols. It will only react with carboxylic acid groups. There are 3 carboxylic acid groups in citric acid. Okay. So for 0.0050 mole of citric acid, we're gonna have 3 times the moles of carboxylic acid groups. So that's 0.015 mole. Now each carboxylic acid group reacts with 1 mole of NaOH. Okay, so for 3 we would need 3 times that. Okay, so in total, that's why I multiplied by 3, because 1 mole of NaOH reacts with 1 carboxylic acid group. So we need 0.015 moles in total. So we know that moles equals to volume into concentration. So 0.015 is equal to volume into 0.40 mole per dm cube. 0.015 divided by 0.4 gives us a value of 0.0375 dm cube multiplied by 1000 is 37.5 cm cube. So the answer is C. 28 is C. Great. 29. The structure By the way, if it was sodium, it would be 4 times, because sodium also reacts with alcohol groups. The structure formula of an ester is this. The ester is boiled with aqueous hydrochloric acid. Check this out. CH3C, CH3H, OCO, CH2, CH2, CH3. I just drew the compound. After hydrolysis with acid, the ester bond will, sorry, OCO, OCO, CH2, CH2, CH3. So after hydrolysis, right, with HCl, we're gonna get this compound over here. And on this side, we're gonna get 4 carbon carboxylic acid. That's butanoic acid. And here, this is a 3 carbon alcohol with the hydroxyl group on the second carbon. Okay, so that's propan-2-ol. Okay, so 29 is B. Last one, the R spectrum of 3 organic compounds are shown. Which one could be the compounds? This is how I solve them. This has a broad peak. It has hydrogen bonding, either OH or COH, and it has a peak at 1700. So it has a carbonyl group. Okay, so that fits the criteria of a carboxylic acid. So probably spectrum 2 is propanoic acid. Now, spectrum 1 does not have hydrogen bonding because no broad peak present, but it does have the carbonyl group. So it can't have hydrogen bonding. So propan-2-ol is out of the question. It needs to be propanone. And look at spectrum 3. It matches with propan-2-ol because it has hydrogen bonding and it does not have the peak for carbonyl. Okay, that's missing. That's why B is the answer. Okay, so that's it. I'm going to be solving the other ones as well in the October-November series. So if you like the video, remember to subscribe to the channel. I'm gonna link ON 2021 variant 1-2 over here, ON 2021 variant 1-3 down here, and I'm gonna link the playlist for paper 1 up here. Okay, so see ya.